Hi, so we will be looking into the question 2 in recitation 7, and that has to do with Kirchhoff's rules. So in the recitation I've already gone through these two rules. Rule 1 is just conservation of charge or conservation of current. So if you've got current I1 here, I2 here and I3 here, this will just give you an equation that will be I1 plus I2 equals I3. And rule 2 says that a sum of potential differences across all elements around any closed loop must be 0. So when you go in a loop, and we'll be doing that soon in this video, when you go in a loop and you add all the potential differences across each elements in that loop, that should amount to 0. That's what rule 2 says. So before we actually do a problem where we will use these rules, we should understand these 4 cases and how we arrive at the answer to what is the potential difference across these things. So these 4 cases, we have got 2 batteries and 2 resistors. Think of this as a part. Let's say this is number 1, number 2, 3 and 4. So in your circuit you will see combination of resistors and combination with different batteries and those kind of things, right? So it is important to know how to calculate the potential difference across these elements, so that when you will go in a loop, right, for rule 2, you can add the individual potential differences to get an equation that will be equal to 0. All the addition of all the potential differences, they will sum out to be 0. So I'm gonna say that, let's say for part 1 we have current coming in here, part 2 current like that, okay, and then in a loop I will be either going clockwise or going counterclockwise. So I'm gonna define delta V to be equal to VB minus VA for each of these cases. For all the cases, delta V equals to VB minus VA, and for all the cases I'm coming in from left and I'm going to the right, okay, because in a loop you will be moving either clockwise or counterclockwise, okay. So because a current is thought of as movement of positive charges, in case 1 what is happening is it's moving from potential, like higher potential, to lower potential. That means VB, potential at B, is smaller than potential at A. So you write down as del V equals minus IR, and we are using Ohm's law, which is V equals IR, or delta V equals IR. When we talk about potential, we actually talk about potential difference. Always think of potential differences. Delta V equals to minus IR, right? So we form this law which says that, it would be nice to write it down here. This convention, it says that our convention is that when moving in the direction of current, the delta V across a resistor is minus IR. So this is important. When you will be in a loop, and then when you go across a resistor, when you cross a resistor, delta V is going to be minus IR for the case of when the direction of travel given by black arrow here is same as the direction of current. So if you're saying this for the first time, it will make more sense as we'll do the example. For just now, you should understand that in a loop you will be moving either clockwise or anti-clockwise, and if you're moving, let's say in our case, anti-clockwise, because you're coming in from left going to the right, and as we are crossing the resistor, we are going in the direction of the current, so we get this potential to be minus IR. The opposite thing will happen if you've got current in the opposite direction of travel. So I'm coming in from left going to the right, and current direction is opposite, so in this case going to be plus IR. Plus IR. You can also look at this equation, delta V equals to VB minus VA. If current is moving from B to A, that means delta V higher potential is VB, so it's going to be plus IR. So there's another convention we have here, and that is copy here, paste, let's paste it here, move these guys down. We have another rule here, another sub rule. Actually, we're talking about rule 2, but we have a sub rule, and that is when moving in the direction of the current. I should edit this out to when moving in the opposite direction. Opposite direction of the current, the delta V across a resistor is plus IR. So we are talking about case 2. Now case 3, again coming in from left going to the right, delta V is equals to VB minus VA, and you see this positive terminal is connected to B and this negative terminal is connected to A. That means B is at higher potential than A, so that means delta V is going to be just epsilon. Epsilon is the potential difference. It's marked as epsilon, this potential difference across the terminals. The opposite will happen. That means that, okay, right, let's write down in English. Coming in, if you're okay, say if traversed in the direction, okay, let's just write down something else, something easier to remember. Potential across battery with epsilon as potential difference. Epsilon as potential difference is plus epsilon if the nearest terminal is negative. So what I'm saying is, if you're coming from the right, from the left, the nearest terminal for you is this negative terminal, right? And the furthest terminal is the positive terminal. So we include the sign of the positive terminal. That's why we have plus epsilon. The opposite thing is true for this case. For this case, if you're coming in from the left and the nearest terminal is positive, that means that potential across battery is minus epsilon if the nearest terminal is positive. So see, what we have done is we have figured out a way to remember these cases. So you can just say that when you're traversing in a circuit and you're moving in the direction of the current, delta V across that resistor will be minus IR. When the direction of the current is opposite, it's plus IR. When you're coming in from the side of negative, then delta V is actually positive epsilon or positive V, depending upon what the potential difference is. When you're coming in from the side of positive terminal, then the potential difference is minus E. So if minus epsilon. So if you remember these 4 points, just 4 points, there are these 4 combinations. If you remember these 4 points, writing down equations for rule 2 will be really easy, and that is exactly what we are going to do now. So problem 2, this is given to you. In problem 2, what we have is, we have got 1, 2, 3 resistors, and we have got epsilon 1, epsilon 2 and epsilon 3 as 3 batteries. So it's a combination of resistances and batteries, right? The very first thing you should do is if it is not already specified to you, like the way it is specified in your homework, you write down the currents in different loops. Okay, so let's talk about point F here, this little node, this little junction F here. If I say this current coming down like this, and I'm going to call it I2, there's a current going this way, I3. There's a current going here, I1. It's perfectly fine if you, so this is the thing, like we specify the currents and the directions, okay? So this is perfectly fine. You can have the opposite directions if you want, because in the very end what we will see in this example is that I3 direction that I have taken is incorrect, because the I3 for me will be minus something. That means that the direction I have assumed is the opposite of what it really is. So that's the only difference you will see, unless the current directions are specified, and then you will have no case but to solve according to those directions. But generally it is arbitrarily chosen, the directions of these currents, okay? So I2, I1, I3. So why I took this special node F, that can be one question. Doesn't matter. What I'm trying to do here is I'm trying to make sure that in each of these circuit elements there's some current going through. So this I3 is same in this section, see? Same I3 is across E3. This is I3, right? So we've got I3 here, I3 here, I3 here. I2 will be same here, okay? I1 will be going down here. So that is why I only specified 3 currents, because 3 were enough to make sure that every element in this circuit has some current through it, okay? So I'm going to delete these arrows for now, but remember this I3 is in this I3, you see, that's like this, going in like that, but only to this point, not through I2. I1 is going through epsilon 1 and R1, R2 is going through I2 is going through R2 and epsilon 2. Okay, so once you have specified the direction of currents, what you do is you figure out what kind of loops do you have, okay? So there's one loop here, okay, loop 1. Loop 1 is loop A, B, C, A, B, C, F, A, okay? Loop 2 is right here. That's loop 2. Loop 2 starts at E and ends at E. E, D, C, F, E. Loop 3 is this big loop, this whole thing. Like if I really want to show you what that loop is, going to be this one. Okay, so that's loop 3. That's loop 3. Now the directions of going around these loops, they're arbitrary. You can choose whatever you want to. Okay, so always that will be the case unless for some reason it is specified in the problem. So it's this bigger loop is A, B, D, E, A. Okay, so there are 3 loops here. Now before even thinking about these loops, let's write down the equation using the junction rule, and that says that at node F, this is what you have. I2 will be equal to I1 plus I3, right? That's what we have seen here. That's what junction rule is. I2 equals I1 plus I3, junction rule. And now we have got 3 loops, and we're going to write down the potential differences across each one of these loops, and using those, writing down when you will get the potential difference across each element in each one of these rules, in each one of these loops, we'll get for each loop one equation, right? So we'll get 3 equations from these 3 loops, and then we have got one equation from the junction rule. So I'm going to call this equation 1 for now, and let's say, okay, now let's talk about this one, A, B, C, F, A. So you start at A, the very first thing you see is that the very first thing we see is that this battery minus and positive, and this is I1. Okay, so we know that if you're traveling in the direction, right, and we're traveling across the battery, the first terminal you see, the opposite of that is the sign of the potential drop, right? So here it was positive and here it was negative. So I'm going to do exactly that here. I'm going to write down the very first thing will be positive epsilon 1. Positive because when I'm here, the first terminal I encounter is negative, and the opposite of that should be the potential drop. Okay, and then I go around this loop, and the next thing I see is this battery I2. So this will be again positive epsilon 2. Positive because the first terminal I see is negative and the second one is positive, so I take the second terminal sign, minus I2, and then minus I2 R2 because I am traveling in the direction of the current. See, there's a I2 current coming down like this, and I'm also traveling in that direction. So that's why it's minus I2 R2. And then to complete the loop, I go from after crossing R2, I need to go to point A, so I go through the resistor R1, and again in that we are traveling like that. So that means the direction of the current is same as the direction of travel. That means again we will do minus I1 R1 equals to 0. So that is the equation you get from loop 1. Okay, I'm going to name that equation to be equation 2. Question 2, of course, question 2. Loop 2, we start at point E. So we start at point E. The very first, I'm gonna be going a little faster here, but this is what I'm gonna do. I'm starting from point E. I'm moving towards point D because loop is E, D, C, F, E, right? So from E to D, I encounter this battery, positive here, negative here. So the first terminal I encounter is positive, so I write down that voltage to be minus epsilon 3. Right, again I come in here, the current isn't moving in the same direction as the travel, so I write that down as I3 R3. For now I'll cross epsilon 2 and it will be positive epsilon 2. Then I'll be crossing R2 and it will be again, actually it will be minus because I'm traveling in the direction of the current. Okay, it's getting a little cramped up here. Let me just write these over here and then make sure that you can see what's going on. Yeah. Alright. Okay, so we get another equation, equation 3. Equation 1 is hanging out here. So now we have got loop 3, and loop 3 starts at point A. So it's gonna be plus because we are moving in this direction, and the first terminal I encounter is negative. So I'll include the other terminal's sign as we have seen in this case. So it's gonna be plus epsilon 1. Then you look at R3 because this is the loop we are traversing, right? Bigger loop around the things that is going in the bigger circle like this. So next one we encounter is R3, then we'll see epsilon 3, then we'll see epsilon 1. So when you use those 4 cases, those 4 conventions that we developed here, you will end up with this equation. Now it is your job to do this, okay? Because I get lazy and this video is already how many? It's nearing in 20 minutes. You don't want to watch really long videos for these things, okay? So epsilon 1 plus I3 R3, this is what you will get, plus epsilon 3 minus I1 R1 equals to 0. So you've got another equation, equation 4. See, this is what we needed. With all this information, this is what we need to go to. We need to understand how to get these equations. Now remember, I have used this as a very general problem, but epsilon 1, epsilon 2, epsilon 3, R1, R2, R3, they are given to you. Okay, because they are given to you, that means that these equations are the unknowns here are only I1, I2 and I3. Okay, so you can figure out those currents. I'm not gonna solve everything, but I'm gonna tell you exactly how to solve these things. Okay, so we have got 4 equations here. Let's bring them close so we can look at them in their whole glory. Okay, so these 4 equations we have, right? Let's do one thing. I'm gonna follow the exact steps that are in your solution. That would be easier for you to follow too. So we're gonna use 1 in 5, and when you do that, that means that substitute. We're gonna use 1 in 2. So we're gonna, in equation 2, we're going to substitute the value of I2, that is I1 plus I3. So you get epsilon 1 plus epsilon 2 minus I2. We're going to substitute the value of I1 actually, minus I2 R2 minus I1 is, from here, I1 is I2 minus I3 R1 equals to 0. Let's call this equation 5. Okay, now what we do is we multiply R3 to equation 5 and then add to that multiplication of R1 with equation 3, and then we get R3. It's your job to follow this. Okay, you literally should do in every step, because as I told you in the class, if you do like 3-4 problems very similar to this, and for sure you're going to see something really similar in your exam. So it's a nice idea to do every step. So it's going to be R3 epsilon 1 plus epsilon 2 minus I2 R2 minus I2 minus I3 R1 plus R1 epsilon 3 R3 plus epsilon 2 minus equals to 0. Let's call this equation 6. You will see that things will be cancelled here, and when you solve this equation, you'll get, we are solving this equation for I2, so you will get I2 equals to, when I say solving equation for something, that something should be in terms of everything else. So that means I2, the answer that you should get is this. And here you know everything. These are in terms of epsilons and r's, which is given to you. So it is your job to solve this. Make sure everything makes sense. And this should give you 18 milliamperes. Now it may happen that there's like a mistake here. I didn't go through the steps myself because they're just algebra. So make sure that you get the right answer. So I2 is equals to 18 milliamperes. Just a point here, because I2 we got was positive, that means that the direction of the current we assumed here is correct. Okay. Now once you've got an I2, you can use equation 2 to figure out I1. So equation 2, use in equation 2. I1 is equal to epsilon 1 epsilon 2 I2 R2 divided by R1, and then you should get 37 milliampere as your answer. Again, we get this answer to be positive. That means the direction of I1 that we chose in the beginning is correct. Now using equation 1, this just tells you that I1 equals to I2 minus I3. You can get I3 is going to be I2 minus I1, and this is minus 19 milliampere. See, this is what I was talking about. You got this answer to be negative, right? So that means the direction of the current I3 is opposite to what we assumed. So that is the only difference you have. You can arbitrarily choose the direction of the loop. You can arbitrarily choose the sense of rotation of the loop, and then when you solve the problem, if you follow the same sign, the same convention that we developed here, these 4 sub rules, these 4 conventions, then you'll end up with the same answer. The only thing that will differ from your answer or from someone else's answer, if they made the opposite choices, will be the sign. And that just means that whatever you have assumed, if you're getting that current to be negative, that is in the opposite direction of what you assume. So this is how you do question 2. Go through this. I'm sorry this video is about 25-26 minutes, but it's good for you. Half of it is what we already have seen, so it should be okay if you fast forward and watch this. And the other is just like, think of it as your investment in the exam coming up.